Okay, so this is our first problem. We're trying to write equations for shear force and bending moment. And we're going to use typical X sign convention from left to right. So I'm going to cut this structure at X. And we've had this discussion for other problems too. You have to decide whether you're going to work the left side or the right side. Now the right side initially has some disadvantages because it's two loads to deal with, that trapezoidal shape. The left side is simpler, but the left side requires us to find reactions. So a little extra work for that. So the first thing we'll do is we'll find the reactions at A, then we'll draw the free body diagram using method of sections of the left side and find the internal shear force and bending moment, and you'll see how that will make it end up being functions of X. So the first thing I want to do is find my reactions at A. So I'm going to assume at A that I have a force AY acting up, AX, and a moment at A. And I'm also going to take this and find the concentrated equivalent of this. So it's a triangle, so it's 1/2 base times height. So that should give me a force of 20 kips. And the distance from A to 20 is how far? Well, it's 2/3 the distance and 2/3 of 20. I'm just going to write that 40/3 right now instead of dividing it out. So the first thing I'll do is I'll sum my moments about point A.
Would it be 20/3?
No, 2/3 of 20.
It's from the left-hand side, you're right. Okay. I was measuring.
Okay. So summing moments about A, I have my internal moment, which I'm using right-hand rule, so it comes out negative. And about A, this 20 kip force also creates negative moment, right? 20 kips times a moment arm of 40/3 feet. So what's the moment at A equal to? Looks like it's going to be negative. What is that, 800 divided by 3? .266.6, is that what it is? 266.7. That would be kip feet. So I got a negative moment, so it's opposite of what I chose here. Then I'll sum forces in the y direction. I got AY up. What else? Oh, minus 20 down. Or 20 down, which is minus. So it looks like AY is 20 kips. And then we'll sum forces in the x direction. And all we have on this problem is positive AX, so AX is 0. So we have our reactions. Any questions so far? So now let's cut the structure and look to the left. I'll try to make this a little larger so it'll be easier to see. So there's my chunk of the structure. And this would be my triangular load. Let's go ahead and put my reactions on this end. So AY is up at 20 kips. The moment at A was negative, so that's going to go this way of 266.7 kip feet. Also, the length of my structure is X. So based on that, What's the intensity of my load right here?
One half x. Wait, no. Yeah, 1/2 x times 2.
What's the slope of the line? Rise over run, right? So 2 divided by 20 is 1/10. So every unit I go over, I go up 1/10. So this should be x over 10. I've basically written an equation for this line. When x is equal to 0, I get 0. When x is equal to 20 over 10, I get 2. So it matches.
Okay, well, can you say that again? How you got x over 10?
That's the slope of the line.
When you just look at the...
Yeah, 2.
Yeah.
The slope is 2 over 20. It's a straight line, so if I find the slope, I've got it. Rise over run, right? 2 kip feet over 20 comes out to be 2. Or 2 kips. No, that's not right. 2 kip feet squared. It's a real funny unit. And you multiply it by feet, you get kip feet. Is everybody with me so far with that? Okay, now the fun starts. If you haven't had fun already. So the concentrated equivalent force, I'm just going to call it F1. What's F1 equal to? Well, we always know it's 1/2 the base times the height. So that's going to be 1/2 the base, which is x, times the height, which is x over 10. So that gives me a force that's x squared over 20. And the distance from the cut to the force is what? The centroid is located how far from the big end? 1/3. 1/3 of the base is x over 3. On the cut, I have my positive shear force and my positive bending moment. So that seems to be my complete free body diagram. And it's valid for any value of x that I choose between 0 and 20.
I know you had mentioned it earlier, but we're just always going to ignore the axial force since it's inconsequential?
Well, there are no axial forces, right? Anyway.
Oh, that is true.
But right, we usually don't deal with it because there's usually... But if there was a horizontal force here, then AX would not be 0, and then we would include the axial force. It's possible. I'm just going to go ahead and write over here that D1 is x over 3 in case you can't see it in here. So now we just do our equilibrium. So I'm going to sum moments about the cut, just like we've always done. So starting here, I get what kind of moment is this with my sign convention? The interior moment. It's positive, right? About the cut, F1 creates what kind of moment? Positive or negative? Positive. So it would be F1, which is x squared over 20, times a moment arm of x over 3. Then I have 20 kips. What kind of moment does that create? Positive or negative? Negative. And what's the moment arm from the cut to 20? X. Then all the way over here on the end, I've got this moment, which according to my sign convention is positive. 266.7. And all the units in this particular expression are moments, so they're kip feet. So now you just solve for the moment. So when I solve for the moment, which is now going to be a function of x, what do I get? Well, all this stuff just goes to the other side of the equation. I get minus x cubed over 60 plus 20x minus 266.7. And again, that has units of kip feet. How do you know that's right? Do you know the moment anywhere on this structure? Well, you know it when x is equal to 0, right? So when you put in x equal to 0, what do you get? You get a negative moment of 266.7. Is this a negative bending moment? Yes, it is. What about the free end? What's the bending moment at B? There's no moment at B. It's free. So if I put in x equal 20 here, what should I get? 0. Why don't you guys check that for me real quick? So I already know that the moment when x equals 0 is 266.7 kip feet. And we checked that, so that's good. We also know that the moment at x equal 20 feet should be 0. Does it come out to be 0? Hey, look at that. So I'm feeling pretty good about this one. Okay, so now let's sum forces in the y direction. Let's see what we get. Okay, I've got my shear force here. It's acting down. I've got my force F1. It's also acting down. F1 was x squared over 20. What else do I have? Well, I've got my 20 force acting up. So when I solve for the shear, it's also going to be a function of x. It looks like I get minus x squared over 20 plus 20. And that'll have units of kips. Do I know that anywhere? What's the shear at A? Well, what kind of force, what kind of shear force is this? Positive or negative? Positive. Right? It's making the object want to rotate clockwise.
Okay.
This is positive shear.
Okay.
So does my equation at x equals 0 tell me the shear is positive 20 kips? Yes, it does. Excellent. What's the shear at B? Which is x equal 20. It's a free end. I don't see anything there, so the shear ought to be 0, right? Does my equation when I put in x equal 20 give me 0? It does. Nice, huh? Now, look at the moment equation and look at the shear equation and think about calculus, and is there a relationship between the two?
The shear is the derivative of the moment.
All right, so it looks like the derivative of the moment with respect to x is equal to the shear. Now, we haven't proven that, but it looks like that's a relationship that right now you could probably lean on. So that's another way to check. If you take the derivative of your moment equation and don't get this one, then something's not right. It doesn't tell you which one is incorrect, but it tells you there's something's not right. So that's two things. You can always check values that you have, and informally, we'll say this relationship is true. I'll derive it next class period. But you can apply that too. So where is the moment maximum? Here's your moment equation. It starts off at x equals 0 at minus 266.7, and it decreases to 0 at 20. So where do you think the maximum is? Just your first guess. Probably at x equals 0, which is the fixed connection. This is a cantilever beam, so the maximum moment occurs at the connection. So a lot of times in cantilever beams, you'll see that they're very thick at the connection, where there's a lot of moment required, and that they taper down to very little moment capacity at the free end because there's very little moment at the free end. So if you see a tapered structure, that's very common for cantilever beams.
So is there any relationship at all between, so like in that case, the moment is highest at the left end and lowest at the right end? Is there any relationship between that and the fact that the load, the distributed load, is greatest at the right end and
No, the moment would still be maximum at the free end no matter what the shape of the load
Okay,
or the
so
fixed end.
that's just coincidence.
Yeah.
Okay.
What's coincidence?
Well, I was just wondering, just because
The maximum moment always occurs at the cantilever, at the fixed support on a cantilever.
Yeah, I was just saying.
Now, in a beam, it's much harder to. Well, not much harder. It's more. It's just more challenge to find out what it is. One more thing while we're here, just kind of thinking about it. Is there a relationship between shear and the loading function? Yeah, if you take the derivative of the shear and change the sign, you get the load. So these things are all related, and we'll use those again to our advantage as we move forward. Okay, I'll stop.